You may have heard that money has grown exponentially, bacteria has grown exponentially, population has grown exponentially. In this lesson, we're going to explore exponential growth and decay. We're going to start with population. And here's a perfect problem for us to demonstrate exponential growth. In 1990, Florida's population was about 13 million. Since 1990, the state's population has grown about 1.7% each year. This means that Florida's population is growing exponentially. Now, this problem was written in the year 2005. So this exponential growth was evident through the year 2005. To find Florida's population in 1991, what you do is you multiply the 1990 population by 1.7%. So you start with 13 million. You're going to multiply by 1.7%. So 1.7% as a decimal is 0.17. But remember, we're going to grow that by 1.7%. So we really have to multiply that by 1.7% and then add that increase to the 13. So what we do is we end up multiplying by 101.7%. And then that's going to give us the next year. And then we're going to take that 1991 amount and we're going to multiply it by 101.7%. And it's going to give us the 1992 population, and so on and so forth. Now, the 101.7% means that you're going to keep 100% of the current population, and you're going to add to it 1.7% growth. So that's your growth percentage, or your rate of increase is 1.7%. And you can see that what I've just explained is right here, 1.7% plus 100%. So here's our function that's going to model that. We have y equals 13. That's our initial population in 1990. Then we have our growth rate, which is 101.7%. I always stumble on saying 101.7. There's no and in there. 101.7%, and as a decimal, that's 1.017. And then x is going to stand for x. Now, it's not multiplied by x. This x right here is an exponent. So that is an exponent. So we want to be very clear that's an exponent. And x is going to stand for the number of years since 1990. Well, what does y stand for? Y is going to represent, y represents the population in millions. Population in millions, x years after 1990. So 1 year after 1990 would be 1991, so our exponent would be 1. 5 years after 1990 would give us 1995's population. Our x value would be 5, and so on and so forth. And that's how you write your exponential growth equation. So here's our standard exponential growth. Can be modeled with the function y equals a times b to the x. I'm going to rewrite everything that they've written here. I'm even going to do it in the same colors that they have. I'm going to try to. Let's see. We got a nice color, blue right here that we need. Okay, so we'll make a, that's our initial value. We should be getting very used to that. That's our initial value. The initial value. We also know that graphically, that's our y-intercept. And then we've got the base, and the base is going to be our growth factor. So that's our growth factor, which will always be greater than 100%, which means that it's going to be greater than 1. And then we have our exponent. That's our input. So depending on what we're talking about, if we're talking about time in days, then it would be the number of days. If we're talking about time in months, years, hours, seconds, it all depends on what it is that you're growing. Bacteria can grow very, very quickly, whereas money might not grow as quickly. It might take months or years for money to grow. So let's model exponential growth when it talks about some money here. Medical care. Since 1985, the daily cost of patient care in community hospitals in the United States has increased about 8.1% per year. 8.1% per year. So increased by 8.1% per year means that we have 100% plus our increase of 8.1%. In 1985, such hospital costs were an average of $460 per day. $460 per day. They've increased significantly since then. So that is where we're starting. So we're starting in 1985 at an average cost of $460 per day. We want to write an equation that models the cost of hospital care that is growing exponentially. So we're going to start with, it's always nice to maybe write the equation down and then go back and make sure that we define our variables very carefully. So y equals our starting amount, our initial cost is $460 per day on average. And then we're going to take that and we're going to multiply it by 100% plus 8.1%, which is 108.1% raised to the x power. Now, two things that we have to look at here. We have to look at this 108.1%, and we have to look at this x power. So those are the two things that we're going to be looking at. What does x stand for? What does 108.1% transfer to or translate to when we're talking about a decimal? And then what does y stand for? So let's take care of the 108.1% first. We have y equals 460 times, we're going to move that decimal place 2 places to the left. So we divide by 100, 1.081 raised to the x power. And now we can define x, and we can define y. So what does x stand for? X stands for the cost of hospital care. It's increasing per year. So that tells us our 8.1% was every year. So x is going to stand for the number of years after 1985. And y is going to stand for the average cost per day of hospital care. So x is the number of years after 1985, and y is the, I'm going to move this so that it's all on the same line. There we go. Y is equal to the average cost per day of hospital care. And there is our equation. So let's box that. That's our equation for A. Now it says use the equation to find the approximate cost per day in the year 2000. So we're going to use this equation. We need to find y. 460 times 1.081 when x is what number? Well, in the year 2000, that's 15 years after 1985. So x is going to equal 15. Now we're going to put this into our calculator very carefully. So you can hit 460, and then you can hit your multiplication button. then in parentheses 1.081, end parentheses, upper caret 15. So you're going to enter that into your calculator just like that, and you're going to get approximately a cost, an average cost per day in the year 2000 of $1,479.60. So they might round that to $1,480. Would not be surprised if they did that. I'm going to pick a pretty color highlighter here. And that's our answer to using the equation that we found in A to actually find an average cost per day in the year 2000. So you can see that hospital care has significantly increased from 1985 to the year 2000. It would be very interesting to take this data and look at what's happening in most recent years. That would be very, very helpful to find out. Okay, let's have you try this. Suppose your community has 4,512 students this year. Student population is growing 2.5% each year. Write an equation to model it, and then find what the student population will be in 3 years. Go ahead and press pause, and when you're ready to reveal the answers, I will provide them to you. Make sure you press play when you're ready to reveal those answers. Okay, hopefully you've pressed pause, you've tried this on your own. The answer to A, let's take that straight tool off. The answer to A is y equals 4512 times 1.025 raised to the x power, where x is equal to the number of years after initial population. They didn't give us a year, so we're going to have to say after the initial population of 4512. And then y is going to equal our total population after x years. And B, our answer using that equation would have been 4,800, approximately 4,859 students. Do you know how many students are in your high school? That is a good question. Do you know how many students are in your high school? Or your community? It could be anything. It could be in your neighborhood. It could be in your city, or your state, or even your country. Okay, compound interest is next on the list. Compound interest. So here we go. I'm going to talk about this one right here. I've got some pretty color going on right here. So I'm going to rewrite it though. So I'm going to make sure I use that pretty color again. Let me just erase that. There we go. Okay, compound interest. Compound interest is when your money makes money. Your interest makes more interest. So you earn interest, and then that gets deposited into your account along with the money you put into your account, and your interest along with your money makes more interest. So that's what compounded means. Suppose your parents deposited $1,500 in an account paying 6.5% interest. Compounded annually. That means every year they look at the balance in your account and they pay you interest on whatever balance is there. Find the account balance after 18 years. So if you do not touch this money, what happens every year is they look at your $1,500 and they pay you 6.5% interest. That gets deposited in your account, and then whatever that amount is, at the end of the year, they look at that total amount and pay you 6.5% interest. So they're paying you more interest each year than they did the previous year. So when you're adding you not only get to keep the 100% of the interest that was there, or of the balance that was there, but you also get an additional 6.5% that the bank gives you. So you get to keep 100% of your money, plus the bank pays you 6.5%. And that's where we get 106.5%. This is growth. And remember that growth is greater than 100%, which means it's greater than 1. So our equation is going to be y equals, our initial amount is 1,500 times the quantity 106.5% raised to the x power. Now that 106.5% is 1.065 raised to the x power. So we have to make that percentage a decimal. This right here is our equation. 1,500 is our initial amount. The 6.5%, that translated to 1.065. And we got that from this addition problem right up here. That led us to the 106.5%. If we just put 6.5%, we wouldn't have growth. See, our growth has to be greater than 100%. Now, what's the account balance after 18 years? 1,500 times 1.065 raised to the 18th power. In your calculator, 1,500 times, in parentheses, 1.065, and parentheses, upper caret, 18. And we get approximately $4,659.98. And there you go. Okay, so here's one for you to try. I'm going to try to delete my handwriting. Had a happy moment right there. Compound interest is a happy thing. You might have just saw the answer, but see if you can try this one. You could rewind it and see the answer, but make sure that even if you saw the answer, let's see if you can get the answer. So suppose the interest rate on the account in example number 2 was 8%. How much would be in the account after 18 years? B, another formula is B equals P times 1 plus R raised to the x power. B is the balance, P is the principal, R is the interest rate in the decimal form. Use this formula to find the balance in part A. And then explain why the two formulas are actually the same. So go ahead and press pause, see if you can come up with the answer, and then press play, and I'm going to do just a little bit of explaining here. Okay, in part A, if the interest rate is 8%, I would have y equals 1,500 times 108% raised to the x power, which is y equals 1,500 times 1.08 raised to the x power. That's going to, and I'm going to make x 18, and that's going to be approximately $5,994.03. So you can see that that little bit of change in increase, let me show you, is a big difference. So your interest rate makes a serious dent in either the amount you have in your savings account, or if we're talking about debt, then the amount that you owe. So important thing for you to think of when you get older and you start having these financial accounts. Okay, B says another formula is your end balance. That's what B stands for. Your end balance is equal to your principal amount, which is 1,500, that's the initial investment, times 1 plus the interest rate as a decimal, and I think it was 8%, raised to the x power. And that's the same thing as y equals 1500 to the 1 times 1.08 to the raised to the 18th power. And you can see it's the same thing. It's the same thing that we had before. So sometimes formulas look a little bit different, but they're not different at all. They're the same. So what is different? What makes them the same? Well, 108% is the same thing as 100% plus 8%, which is where we get the 1 plus the interest rate of 8%. 1 plus 0.08 is 1.08. 108% is 1.08. Same thing. So that is why A is the same thing as B. And you can use whichever formula you want. As we move forward with compound interest, we're going to look a little bit more at this type of formula in B, and you'll see why. And that is because when the bank pays you interest, it's not usually annually. They're usually looking at your account a little bit more frequently than annually, which gives you a better opportunity to earn more money.